Next, we're going to move beyond point estimates and begin to consider a confidence interval. What if we actually want a range of likely values to that we're of what we should expect for the population mean? We're trying to make assertions about a population mean. We may be able to come up with a best guess, but an interval and say we think the mean must lie somewhere between this and this is also something that we very often want to do. So so we use confidence intervals to provide an interval estimate of a distribution parameter rather than a point estimate like we were considering in the last section. Um, the confidence interval that we come up with would be associated um, uh, with the confidence interval that we'd come up with would have an associated confidence level, which would be written as gamma, or more commonly 1 minus alpha. And there are several different types of confidence intervals, and we're going to consider several. But you're familiar with these, where somebody probably spoke to you in the past about a 95% confidence interval or a 90% confidence interval. And that's how what we're going to be aiming to produce. When we define the confidence interval, there is an actual formal way to describe it and a more common um, way that people consider what a confidence interval means. If we take samples from a population that is normally distributed, more or less, we may want a confidence interval about the mean. If we know the variance, which may come from previous experience, we'll use one particular method for the confidence interval. If we don't know the variance, we'll use a different method. So the choice of which kind of confidence interval to use will depend on what we know already about the variance of the population. When we describe confidence intervals, we need some critical values. And since one of our assumptions in this application is that our population is more or less normally distributed, we're going to come up with critical values that came from the normal table that we were introduced to in the last chapter. And some of these values you've seen before, but if we're looking for a 90% confidence interval, we might need the z critical value of 1.645. 95% confidence interval has associated with it a 1.960, etc. You'll need these numbers, and they'll be available to you in the equation sheet that you will have to use on the final exam. When we describe the two-sided confidence interval, or the z interval, this means that we're dealing with a case where we have a known variance. So this is the appropriate confidence interval to use when we know the variance. Somehow you'll need to be given that information that the variance is known. So always be on the lookout for problems where it's got a known variance of this. Then once you know that variance, then you know, I need to use a z-table. And so this is a two-sided z interval, or two-sided confidence interval for the case of a known variance. In that, you can say that we expect the mean of the population mean, that is, to lie somewhere between x bar minus zc sigma over the square root of n, to the upper end of the interval is x bar plus zc sigma over square root of n, where n is the number of observations in our sample that we had, and that sample is where we came up with the value of x bar. So we can get this two-sided confidence interval once we know the sigma, and that is going to have to be given to us. We'll have to find the x bar of our sample, the sample mean, and the number of observations in that sample, and we can then construct the two-sided confidence interval. The ZC that we use. The ZC should depend on whether somebody has asked you to find the 99% confidence interval or the 90% confidence interval, etc. More on what level of confidence to select if you're ever given a choice is we'll talk more about that in another section. For the case of an unknown variance, again, the previous case involved a known variance, but now if we have an unknown variance, you don't know that much about the population, and this is the most common case. In that case, we can't use the normal table and the z values. Instead, we have to use what's something that's called students t distribution, which is available to you as table 25-2, and it requires a new parameter you haven't used before, which we'll define as n minus 1, and that's the degrees of freedom that are affecting our sample size, or it's dependent on the sample size. Here's an example of what a t-table looks like, where we'll need to know our number of degrees of freedom, and with that we can then look at the CDF, the F value that we're looking for, and from that we can get the value of the t distribution that we need. Now it's this set of t numbers here from the table that we'll actually want to construct something like a confidence interval where we had 8 observations, which means our number of degrees of freedom is 7, will then have the appropriate value of t to use to construct our confidence interval. And here is the two-sided confidence interval, the t-interval, for the case of an unknown variance, where instead of having a sigma that somebody has told us from previous experience we know what sigma squared or sigma is, instead we're going to have to use our sample standard deviation s. Now here, notice that in this confidence interval, we're reminded that we need to use a t of alpha over 2. Thus, if somebody told you to use a 95% confidence interval, you'd look up the alpha for 97.5 and n minus 1 and come up with that t value. Multiply by s, divide by the square root of n, and then use that value as x bar plus that and x bar minus that. Those are the two sides of the confidence interval. That's also known as the two-sided unknown variance case. How do you select which of those methods is correct? You must answer each of these questions. If you are told that you know the standard deviation or you know the variance, then you know sigma. So the first question, is sigma known? Then you have to ask the question, is n greater than or equal to 30? If n is not greater than or equal to 30, then you can have to ask the question, is the data more or less normally distributed? And then you last have to ask the question, do you want a one-sided confidence interval, which you might also call an upper or a lower bound estimate on the parameter, or do you want a two-sided confidence interval? Sometimes we care only about one side, being wrong in one direction. Sometimes being wrong in either direction is equally unwelcome. When we care about being wrong on either side, we certainly want the two-sided confidence interval. Most commonly, at least in this class, I'll be either telling you you want the one-sided case or the two-sided confidence interval for a particular application. So, now that we know all this, which method do you use? The fourth point is relatively straightforward. You either want the two-sided confidence interval or you want an upper or lower bound. In the answer to the first question, if you are told that you know the standard deviation or know the variance, then you know sigma, in which you should be using the z critical values and that first type of confidence interval that we described. If n is greater than or equal to 30, then you don't care whether the underlying distribution is more or less normally distributed. You have a large enough sample that you can go ahead and use the student's t distribution in order to come up with your confidence interval. If n is less than or equal to 30, then you need to be given information about whether the underlying population is more or less normally distributed. If it's more or less normally distributed, then you can go ahead and use the student's t-distribution and proceed. If you have reason to believe that the underlying population is not normally distributed, or you can't make any sort of convincing case, then you really don't have an option. You'd have to wait for one of the sections later in this chapter when we talk about nonparametric methods. So we can really only handle a case of known variance where sigma is known, or n is greater than or equal to 30, in which case you're using the student's t-distribution, or it's less than 30 and it's more or less normally distributed, and then we've got some one of the methods we can use. But if you don't have a normally distributed population and n is less than 30, then you're out of luck. You've got no method that you can use that we're going to be introducing in this section. Sometime our choice on the level of confidence means that we're going to lengthen or make our confidence interval wider. If you want the 99% confidence interval, then you're going to have a very wide interval. If you want the 90% confidence interval, then it's going to be much narrower. One of the most common ways that people interpret a confidence interval, and it's not the most accurate, but it is one of the most common, is that people often assume that a 90% confidence interval means that once you've defined the interval, is that you are 90% certain that your population mean lies within that range. And that's not quite right, but it's close enough to being right that it's pragmatically useful, and that is the thing that most people normally hear about it. What the confidence interval actually means is that if you collected a large number of samples of that size, that if you've calculated the 90% confidence interval, 90% of your samples will fall within that range. That's a very esoteric definition, and most people don't prefer it, even though it probably has slightly more credibility than the interpretation that most people make, and that is that we're 90% confident that the population mean lies somewhere in that interval. And so if you go ahead with that interpretation, I'm fine with that, and so is your textbook. Sometimes we'll want to narrow the confidence interval to a specific size L. If you do that, you can use this equation to help you estimate the number of observations that you should make in order to get a confidence interval of that size. So if you want to say, I want to know the answer to within 2%, then you've defined your L size, and you can calculate how many observations you'll need to collect in order to get a confidence interval down to that size. Using this type of thinking, if you were collecting information about polling results of who's likely to vote for which candidate in an election, you could use this type of formula to decide how many people you need to have in your sample in order to get an estimate of how many people are going to vote for a particular candidate within 2%. And you could then have L be equal to 2% and decide how many voters you need to go ahead and include in your sample. This equation isn't exactly what we would use for polling an election, but it is something that you could use if you were trying to figure out the strength of your particular material and wanted to know the strength within a certain confidence interval of size L. So this is useful for deciding how many samples we need to collect. When you're asked to help design a sampling plan, this is the type of calculation that you might want to include to have some estimate on how narrowly you want to define the parameter that you're getting after and define your confidence interval with that particular size in mind.